Page I full up my computer with recording. Yeah, good. So um, I trust that the two videos I sent two videos to y'all last week. There was the power outage, and um, I just can't have enough power to power all these. Well, I got some a desktop computer, right? So I can't see on my laptop; it's too small. Um, so I couldn't, have a class with no power. So I sent two videos. They were all videos, but those were the videos I recorded when I think it was COVID. Um, were you able to watch them? Anybody was able to watch them? And any
Yes, sir.
comments as to whether they
Yes,
were
sir.
useful? You thought that you learned something from something? Hmm?
Yes, sir. I was able to more understand quadratic. Like I know how to do it, but that video helped me to more understand it.
Okay, all right. Yeah, all right. And quadratics for you, I mean, the students in this class should be more of a revision topic, right? When I watch some of your grades, I see a lot of people get grade one in mathematics, grade twos, just a few of you. I think there's hardly five students in this class who got grade threes. And even so, you should have been exposed to quadratics, quadratic equations, solution by factorization, and completing a square formula. So it should be more of a revision, right? And I hate when, students are taught something first form, they forget it. That you teach them again second form, they forget it. That you do it again third form, you do it again fifth form, fourth form, and fifth form, they still ain't know it. What is the likelihood that you will ever know it if you know you're showing the thing over and over and you're not getting it? Um, the problem might very well lie in the effort you were making to make sense of the topic. Anyway, I hope that you have watched the videos and benefited somehow. So I can't remember if I touched on this matter here, right? And this is something new. This is something new, right? Um, in CXC or your CXC level, you are not told, or you didn't study this aspect of quadratics, right? And let me just use the quadratic formula, right? That okay, if you were to solve, okay, if you have an equation of the sort, you have to solve ax squared plus bx plus c equals 0, then x is minus b plus or minus the root of b squared minus 4ac all over 2a, right? You know that formula well, and perhaps you know how to substitute inside if given an equation to solve a quadratic equation, right? Especially when the quadratic doesn't lend itself to um, factorization, right? And even a lot of people shun away from completing the square because it's quite a difficult concept for most, but it's very good. It's good. That's a concept that is good for your cognitive development. It got you to think different ways of things. The arithmetic involved, and so that property of perfect square. Those are interesting things that really bend your mind. A lot of people, they're just like that formula in the textbook, right? There's a formula where you can know, what to put at the end there and all of that. But if you understand the concept, it's very good, very good. Anyway, let's come to this formula, right? Because this formula can tell us quite a bit, right? It can tell us quite a bit. And in particular, we're going to focus on, and please don't scratch on the screen because I can't get it out. Remove this blue scratch I'm seeing on the screen. Yeah. I want to focus on the nature of the roots. All right, let me zero down on the roots, right? Of a quadratic equation. Because understanding the nature of the root can really help you with getting a visual concept of the graph of the quadratic, right? Um, just to let me just put a graph here, So you might want to know, well, all right, does the graph cut the x-axis two places like this here? Does it cut, you know, down here, right? Do you have two distinct roots or solutions to the equation, right? At other times, if I am to go here, you can have a quadratic just touching the x-axis. Does it look like a touch, or I didn't quite touch it? It should touch, right? Yeah. You want to know, does it touch like that? Does it touch like this? Just touch. Oh my, touch. Or like this. Let me draw it better here, man. Like somehow I'm not good with drawing with this tablet. Yeah. Does the quadratic graph just touch the x-axis? Does it cut like that? And then you can have the situation where it doesn't touch or cut the x-axis at all. Let me go here. You can have a quadratic where it's just there, or there, right? Or there. It doesn't cut the x-axis at all, right? How do you know that? How do you know that? Right? All those things can be determined from this formula. Let me go back to the formula. This formula here, right? This formula here. In particular, um, what is happening here, right? What is happening with this expression here? B squared minus 4ac. Let me erase the graphs, right? Um, B squared minus 4ac. Have you ever, or at CXC level, give a name to this expression B squared minus 4ac at CXC? I didn't give it a name. This
No,
expression
sir. No, sir.
B squared minus 4ac, right? It's called the discriminant. Discriminant. Sound like a criminal. Criminant. I hope the word spelled right. Discriminant. Right? It discriminates. It can actually tell you, right? It can actually tell you a lot about the quadratic, in particular, the nature of the roots, right? The nature of the roots, as the heading is saying, right? And what you will find out is that, okay, if b square, I think I did give you some notes on this, huh? If b square minus 4ac is greater than 0, right? It means it's a positive number, right? Let me write that. Um, is a positive number. That is what I mean by that. Positive number. if this here is greater than 0 or it's a positive number, well, then what you will have here, you will have the square root, okay, x then will be equal to minus b plus or minus the square root of some positive number over 2a, right? So the square root of any positive number will give you two values, that's all. The positive square root and the negative square root, right? And therefore, the notes, if you read it well, you will see that, well, if that's the case, if b squared minus 4ac is a positive number, this you will have the square root of a positive number, which will give you two values, and you're going to get what they say two real distinct roots, right? Meaning you'll get two solutions. You'll get two solutions, right? They're going to be real numbers. They can be negative and positive, fraction and all, but they're going to be real, right? And they're going to be different, right? You get that?
Yes, sir. Yes, sir.
Right. So maybe if you want to try one quickly, you take let's take one. Let's say you have, all right, x squared. You have to solve this, right? Solve what, x squared plus 5x plus 6, equals 0. You put that in the formula. X then is equals to minus 5 plus or minus the root of 5 squared minus 4 times 1 times 6 all over 2, right? If you work this out, you're going to get what? Minus 5 plus or minus the root of 1, right? You think so? So you have two solutions there because it's either minus 5, x equal minus 5 plus root 1, which is 1, right? All right, let me put an extra step here. Minus 5 plus or minus 1 all over 2, right? So either minus 5 plus 1 over 2, x equal that, or x equal minus 5 minus 1 over 2, right? So you have two distinct solutions, right? I guess you can simplify that, right? So you get two solutions. The reason why is that this expression under here, b squared minus 4ac, happens to be a positive number, right? So you get two real distinct solutions, or roots you call them, right? Get used to that word, that term too. Think you get it? All right. The other case, so in other words, let me just clarify that. In that case where you have two solutions, your graph, you know that your graph, what were the solutions? Let me go back. What were the solutions? 5 minus 5 plus 1, you are minus 4 over 2, which is minus 2. Okay, and this one is minus 6 over 2, which, okay, minus 3. So your solutions are, okay, minus 3, minus 2. And the fact that the thing had a positive value in front, x squared, the graph looks like this, right? Something like that. And goes up through there and go up back to, I think down here got to be 6. Was there a 6 at the end? Yeah, right? So the graph passes through there, right? Y'all know why the graph shaped like a U and not this way, right? There's a thing about if any coefficient in front here is positive, the coefficient of x squared is positive, you get what you call a minimum graph, right? Or a U-shaped graph. When it's negative, when you have negative x squared, the graph looks like this, right? It's concave down, right? Follow me so far?
Yes,
Yeah,
sir.
yes, sir. Yes, sir.
All right, good. So let's talk about when b squared minus 4ac is now equal to 0, right? When that happens, what basically happens now is that you end up with, remember the expression x equal minus b plus or minus. Well, remember, if this part here, if this part is 0, then the thing turns out to be minus b over 2a. And that's one number, right? That's one number. Is that clear? Yeah, so you would have one solution, right? Sometimes you hear the books will say it has equal roots, equal roots. Sometimes you will hear about a double root, double root. Some books will say that. I like to say there's one root. I like to say that because, just saying, what do you mean by equal roots, right? I think where they got that from is like, okay, let's take one. Let's say you have to solve x squared plus, let's go with 6x plus 9 equals 0, right? So, all right. If you were to use the formula, okay, before this you can factorize, right? This is x plus 3 all square equal to 0, right? So, I think, okay, this means this. So I don't know why people are so, okay, do it twice. X plus 3 equals 0. X is equals to minus 3. No need to do it for the second bracket, right? But I guess that is why they say the roots are equal, because both brackets is the same thing, right? So there's no need to say that, you have a double root or the roots are equal. There's one root, right? Minus 3, right? But if you were to use the formula now, let's use the formula. Let's use the formula. So x then is going to be equal to minus 6 plus or minus the root of what? 6 squared minus 4 times 1 times 9, right? All over 2. So you see what happens under here? All of this turns out to be 0. So you're left with minus 6 over 2, which is minus 3, right? So whenever you have a situation where 4b squared minus 4ac is equal to 0, you have a single root. As a matter of fact, this condition, b squared minus 4ac equals 0, is the general condition for perfect squares. Perfect squares, right? Is a general condition, right? Let me just explain what I mean. Like when you have, or we had that one just now, x squared plus 6x plus 9 equals 0, right? There's this thing that when you have a situation where half of the coefficient of x, when you square it, you get this number at the end. They say, well, look, you now have a perfect square, right? But if you were to have a coefficient in front here, let me see if all right, let's say I have this 3x squared plus 6x plus 9. Not 9, 3. Let me go with 3 equals 0. Right? Now, is that a perfect square? It is, right? I think so. Yeah, let me see. It's 3 bracket. This is a bad example, right? But I'll just show you something. 3. So it's 3 times x plus 1 square, right? So it is a perfect. It's a bad example. I know that. But in this case, half of 6, when you square it, you don't get 3. Right? You don't get 3. So that thing where, we say that half of this and you square it, you get 9 at the end here. That's a condition for a perfect square. It only holds when the coefficient in front here is 1. But in this case, you do have a perfect square, right? But that condition doesn't hold. But the general condition hold. Because watch. B square minus 4AC. But for this one here, right? You have what? 6 square minus 4 by 3 by 3, which will give you 0, right? So that this condition here, b square minus 4ac equals 0, is the general condition for a perfect square, right? When a quadratic is a perfect square, b square minus 4ac equals 0. And the graph, what was it, minus 3? The graph looks like this for that function here. I'm talking about x squared plus 6x plus 9. All right, so the graph of this function here looks like this. So let's say minus 3 is here, minus 3. Graph looks like this here. Oh, forgive me for this horrible, oh my. All right, let me, yeah, let me try one more time. Yeah. So let's say, 9 is there and minus 3 is there. So the graph comes like this, right? Touches a 3 and goes up back, passes through 9, right? All right. I have to move my 9. I have to move my 9 to suit my drawing. Yeah. So your graph touches the x-axis just one place, right? It touches it one place. You get it now? Good. Let's go to the last situation. And the last situation when b squared minus 4ac is less than 0, meaning a negative number, right? A negative number. Right? When that happens, well, look at what is going to happen. Let's take a quadratic. X squared plus 1, right? Equals 0. And you do this now, look at what happens. So you get x equal, well, you can solve this directly, right? You can solve this like this, right? X squared equal minus 1, x equal to the square root of minus 1, right? You can do it that way, or you can go with your formula. Well, there's no b term here, right? So there's no b term, so you get plus or minus the root of, well, again, there's no b square, right? 4 times, what's happening there? A 4 times, am I going right? A times 1 times, oh gosh. Times 1, right? All over 2. So we can end up with what? No, I have to get 0. 0 minus that, right? Because there's no b term. So here you end up with plus or minus the root of minus 4 all over 2, right? So you end up with a big problem there. Because so far in the course, we have not talked about how do you find the square root of a negative number, right? Square root of a negative number. We haven't talked about that, right? So we have a situation in our hand where we're yet to explore mathematics, right? That will tell us, well, how do we calculate the square root of a negative number, right? And if you read the notes and so, they'll tell you that, and I'll just give you a little glimpse that when this happens, right, you have what we call complex roots, right? Complex roots. And in time, in this very course, we're going to be introduced to what we call complex numbers, right? Imaginary and complex numbers. We're going to be introduced to those, and well, we'll have a little more understanding of this, right? So whenever this happens, though, b squared minus 4ac is less than 0, just remember that you'll have a situation where, okay, like in this case, square root of a negative number, though here, same thing, square root of a negative number that we're not certain how to handle at this point, right? So our root is complex. And if you were to throw this on a diagram, right? If you were to throw that on a diagram, basically that particular, of course, if you want to use Desmos to graph x squared plus 1, right? When you go on Desmos, you got to graph this, y equal x squared plus 1. What will happen? Where 1 is here, this graph comes like this, right? And goes up back, right? Not exactly at 1, but yeah. Comes down to 1 here and goes up back. It doesn't cut the x-axis, right? Doesn't cut the x-axis. Got an idea there? Good. So we want to move over to something that is, again, related to quadratics. But it's a little new for you, right? Because you didn't you weren't exposed to this in CXC or so. Again, the whole purpose of this is to bend your mind a little, right? To bend your mind a little. Some people say, "Sorry, man, what you doing? You're going into more quadratics. When we ever use that in my life?" I told you already. You're not doing algebra, for the utility of it. You're doing algebra to develop your thinking ability, right? To understand complex things, right? That's what you're doing it for. So what we want to talk a little bit about now is the relationship, and I think the notes got it, right? Relationship between um, between the roots and coefficients of a quadratic, oh gosh, quadratic equation, right? I'm going to use on my equation. If you read the notes, you'll see this heading there somewhere. All right, and they did something interesting that we want to talk about. Given the roots of an equation, and here is where that backward, let me not use the word backward, reverse engineering the equation or the function. It's a useful skill, right? Throughout your study of quadratics, what were you doing? Right? You were given some quadratic expression, and maybe you have to factorize it or complete the square and find some root of the equation. What about if you were given the root and you have to find the equation? Let me ask you. Let me just ask you this. I say, look, write down the equation, and I mean the quadratic equation, right? Quadratic equation with roots -2 and +3. If I ask you that, can you do that? If I ask you something like that, I gave you the roots. I don't want you don't have to find the root now. I gave you the root. I'm asking you, what's the equation? Anybody can say? And here's where you know that being able to think in reverse, the very difficult, ability. Think about it. All of you know ABC, right? Right down to Z. How many of you can recite the alphabet from Z to A? Very difficult. Anybody can do that in the class?
No, sir.
Very, very difficult, right? So that reverse engineering, I like when I do calculus, and when we do differentiation and then something named integration, and integration is the opposite of differentiation. And I always use in nursery school, they used to talk about, there's a rhyme called Humpty Dumpty sat on the wall and Humpty Dumpty had a great fall. Everybody knows that, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
Who or what is Humpty Dumpty?
An egg.
Yes, yes. It's easy to break an egg. You know of anybody or that can put back the egg together, right? So that's the whole moral behind the rhyme, Easy to break things, easy to get into trouble, right? Get out is another problem. To put things back together is another problem, right? And that is why that ability to put back things together, police in this country, you go to a cinema and down there piecing back the events leading up to this man's death, up to when they find him. It's that's why for me I like these detective shows. Um, I watch them a lot, right? Law and Order, Mentalist, and so those are the kinds of, because the reverse engineering that these guys do, I mean, it's just a show, right? Um, there are people who do it in real life. It's a skill by itself, right? So yeah, being able to take the roots now and get back the equation, right? So it shouldn't be hard. If the roots are that, what? X plus 2, x minus 3 equals 0. Isn't that what led to that? And then you can remove the bracket and get the answer, right? I don't have to do it. So you'll have what? X squared, what is it? Minus x minus 6 equals 0. That's the equation. I hope so. Right? But notice how you got the equation. If minus 2 is the root, then one of the factors of the quadratic function was x plus 2, right? And if 3 is one of the roots, then x minus 3, right? Notice I use the opposite sign here, is one of the factors of the original function, right? Y'all get that? How we do that?
Yes, sir.
Yeah, right? Let me throw another one at you. Let's say you have that one was easy, but let me throw another one at you. Maybe, all right, let me go with -1 and a half. Boom. What are you gonna do there now? Any thoughts? No thoughts whatsoever? Give me one part. Okay, let's start with, all right, this here, this here, this here equals 0. Give me at least, what should I put here? Given that the root, one of the roots is -1. What do you think I should put here?
X plus 1.
Great. Yeah. What about this one now? X
Minus 0.5.
minus
Or
a half.
minus
All
half.
right. Well, you ever see this? You never see this, right? But remember, you can multiply all both sides of this equation by anything you want, right? So let's say we multiply by 2, right? What will happen? You get x plus 1 times 2x minus 1 equals 0. And if you were to solve this, wouldn't you get this?
Yes, sir.
Right? And so that's the kind of reverse engineering, right? That's the kind of reverse engineering that, if you can master the ability, I'm not talking about mathematics, right? If you can master the ability of reverse engineering, you could do a lot of great things. As a matter of fact, the Chinese are great at that, right? What is happening, and yes, the Americans are accusing the Chinese a lot, right? That's what they do a lot. People go there and say, look, I want you to make this thing, right? And lots of times the Chinese, okay, let me skip that part about people going to them. They see a product in the West and they want to knock it off. What do you think they do? They go, they buy the product, and they take it apart. They take it apart and they see, oh, this fits with this and this fits with that, and they know how to replicate the thing now and make their own product, right? And it doesn't have, well, all them phones, and so yeah, I'll use all make in China, right? I've seen how they counterfeit the things. People make a phone, it looks like an iPhone, and it just paste on the logo or print on the logo, right? So that ability to reverse engineering things is quite an ability, right? It's quite an ability. I remember telling, y'all have a lecturer named Adrian.
Yes, sir.
Yeah,
Yes, sir.
and a few years ago, when we didn't know about Zoom and so then, right? This whole Zoom thing and teaching online and all of that was unknown to us. Before COVID, let me tell you something, among the things I learned during COVID to now, I cannot believe. I cannot believe. I have really been pushed to the limit, and I've done some remarkable things that I didn't think I could have done. Right? But anyway, before COVID, lecturers started to develop a liking for whiteboard markers. They didn't want to dirty their hands with chalk, and they come, especially the female, they dress up so fancy and they want no dust go on their skin and their makeup and all kinds of things. So they're fancy whiteboard markers. And I was telling Adrian that if we in Guyana, we can crack the ink, right, for whiteboard markers, and we can reproduce it, we'll get a big contract with UG because we were using whiteboard markers by their hundreds every week. We never got markers. Every day you come to the classroom, marker done. You're watching the bin 10, 12, because each lecturer, by the time you finish a lesson, 2 markers or 3 markers finish, right? And I actually saw a guy who reverse engineered the dry erase ink on YouTube. I was showing him it, and I was telling him, well, we can actually copy this and make our own ink here, dry erasing that is, right? And we can even refill the markers that we're using at UG. That skill of reverse engineering. You take the thing and say, well, what is this thing made up of? How do you make this thing, right? And that's a great skill, right? As a matter of fact, After some time, and let me see if I can find it here. 1 second. I actually bought some markers from China where the people send me some little bottles of ink that you can refill the dry erase markers. I have it until now. I bought it like 7, 8 years ago. I kept it as a souvenir. I bought a red, a blue, and a black. And I have the bottle of ink. As a matter of fact, somebody asked me to stamp their timetable the other day. I had no ink. I just used the ink on it. But it's a dry erase ink, right? The only difference between the dry erase ink and the regular ink is that the one that mark permanently, right? Any chemistry people in this room? No, there's no chemistry people in here. Oh gosh. They put a binder, right? So that the ink will bind with the paper or whatever you're writing on. However, in the dry erasing, they don't put a binder. They put alcohol instead, right? So that what happens when you write with the thing, the alcohol vaporizes and leave the pigments. And the pigments, they have magnetic property, right? So what they do, they put something magnetic inside. So when you take the eraser, the eraser is also magnetic, and it sucks out the pigment from the board, from the whiteboard. Remarkable. But we could actually reverse engineer something like that and be able to replicate it here. It's a useful skill, right? I know it sounds very relevant from what we're talking about, but this is what we're talking about. Being able to reverse engineer things. Good. So let me get into the notes I sent you on the same subject here, right? And okay, let's say we have some equation, ax squared plus bx plus c equals 0. And the roots of this equation, they're alpha and beta, right? Most textbooks will use alpha and beta. Some of them might not use that, but I'm yet to see a renowned textbook that doesn't use alpha and beta. Good. So basically then, if alpha and beta are the roots of the equation, then the equation basically is x minus alpha and x minus beta equals 0. So these two statements here they're equivalent. They're equivalent, right? So if we are to compare them, and this is what we'll do, right? We're saying that, okay, x minus alpha times x minus beta, let's say they're equivalent, right? Ax squared plus bx plus c, right? But they're identical. So what we'll do, we'll take this here and divide everything by a, right? So you're going to end up with x squared plus b over ax plus c over a. And if we were to do a comparison, right? Let's see, what do you do? I'll take this, right? If I were to remove this bracket, I'll get what? X squared minus beta x minus alpha x plus alpha beta, right? So I can take this x squared, I can factorize out here, right? And I wouldn't put the beta in front of the alpha, put alpha plus beta x plus alpha beta, right? So look at this here, right? If I were to compare these two expressions now, what do you see? What you're seeing is that some of the roots, remember we said alpha and beta are the roots of this equation. So the sum of the roots, right? Alpha plus beta is equal to minus b over a, right? How I got this? I compare this and this. So watch here. Let me move this thing a little. I just want some space. So here I have minus alpha plus beta is equal to B over A. B over A. So I can rightly say that alpha plus beta equal minus B over A. Right? So if you are given the roots of a quadratic equation, you can don't know, right? What is A, what is B. Similarly, if you were to compare these two equations here, two expressions, alpha beta equals C over A. Alpha beta equal C over A, right? And these two relationships can actually help us to figure out what the original equation was, right? I actually showed you just now with the 2 and the minus 3 and the half and so on, right? I actually showed you that. So knowing the roots, you can reverse engineer the original equation. That's what I'm trying to get at, right? And the rest of the notes I sent to you now just went into it went into doing some kind of manipulation with alpha and beta, right? For example, let me just borrow, I'm going to borrow an example. Let me borrow an example. Some of them are very involved. All right, let me borrow this example. One second. Look at this one, right? So here, they didn't actually tell you the roots of the equation and tell you to engineer the original equation, right? They didn't do that. They ask you for something else, right? They're asking you for the values of 1 over alpha plus 1 over beta and 1 over alpha beta. And from that, they're expecting you to write down another equation. They want you to find another equation. But that equation has roots 1 over alpha and 1 over beta. Right? So they don't want you to engineer this equation. They already give you it. They want you to engineer another equation, right? And that equation, the roots are 1 over alpha and 1 over beta. Right? So you think what they're asking us? We don't have to engineer this equation. They give us the equation. They want you to figure out, well, how can you get the values of this and this? And after you have done that, find the equation of a whose roots are these. Good. So how do we do that? Good. So what is the first thing we want to do? We want to find, let me just give you an idea. You might want to know, well, how the hell can I find the value of 1 over alpha plus 1 over beta? And if you didn't see an example before, you will never, let me not say never, it is very unlikely, right, that you will be able to do it. So they want the value of this. So you can't just leave it like that, right? There's no way you can find the value of this by just leaving it just like that. So what you want to do is use your little bit of algebra. I think I need to make this thing a little bigger. One second. Can't do anything about that. All right. Okay, I'll try to make this space thing. Yeah. So you can't find the value of 1 over alpha plus 1 over beta directly, right? But there is a trick. There is a trick, right? And I'm going differently from what a book has. You can always read that and, you know, but you might be wondering, how do I find this value, right? And that's where, you know, your problem solving ability is going to kick in now, right? So don't just stare at it. What can I do to this? Maybe I can add them up, see what happens. Let's see. So, you know, you find your LCM, alpha, beta. Okay, that looks like something familiar. So how will you do? Alpha into alpha beta is beta. Beta by 1 is beta, right? Plus beta into alpha beta is alpha. So alpha by 1 is alpha. So look at what you get here. Let me write it back in a familiar way. Alpha plus beta over alpha beta. Now you just found out how to find alpha plus beta and alpha beta from this equation. Remember that? So we're going to take this equation, divide it throughout by 2, and you'll get what? You'll get x squared minus 7 over 2x plus, well, I wouldn't put 4 over 2, I'll put 2 equal 0, right? So the equation, the original equation becomes this, right? And if alpha and beta are the roots of this equation, then what did we say earlier? Alpha plus beta then will be equal to what? Will be equal to, remember, minus of this, which is 7 over 2, right? So we have a value for alpha plus beta. And we also know that alpha beta is this number here, right? 2, right? So watch this expression now. Do you see that we have what we need? So 1 over alpha plus 1 over beta is the same as this, which is equal to, so alpha plus beta over alpha beta, right? Or I should, let me write it differently. So 1 over alpha plus 1 over beta, which is equal to alpha plus beta over alpha beta, is really, what do you find this to be? 7 over 2 over 2, right? And what will that be? 7 over 4 now? So we got a value. We got a value for 1 over alpha plus 1 over beta. See that? And then they ask you for 1 over alpha beta, right? So remember, we got alpha beta here is 2. So 1 over alpha beta will be 1 over 2. So we solve half the problem there. We solve that star. You see? So sometimes you see the thing, you don't know what to do, right? You don't know what to do. But I guess this one here, 1 over alpha beta, you might figure out, you know what, I can get alpha beta, right? But when you see this, you want to know, how do I find this? But with a little bit of algebra, and that's the next thing, right? When you have to solve a problem, don't stare at it, right? Don't stare at it, right? Try the problem. Think about what are some possible things you can do. Like this one here, you watch it, say, how will I get this? You know? But you can ask yourself, maybe I could add the thing using my knowledge of fractions and see what happens. And look at when we did that, what happened. We end up with something very familiar. We got alpha plus beta, which we can pick out from the equation. And we got alpha beta, which we can also pick out from the original equation. And therefore, we could have cracked what 1 over alpha plus 1 over beta is and 1 over alpha beta, right? So we got those. Maybe we should write that down somewhere, right? So we got 1 over alpha beta, all right, 1 over alpha plus 1 over beta, which is equals to alpha plus beta over alpha beta equal 7 over 4. And then this here, right? 1 over alpha beta equal to a half, right? So we can erase everything else because we want to tackle the second problem here. I'm not getting any feedback if people are following it.
Sir, I'm following.
Following. Good. So now I needed more people to say whether they have any idea what I'm doing. I'm not getting anything from anybody else.
Sir, I don't have any idea.
Sir, I have no idea what you're doing. I'm clueless.
I'm so lost, sir.
Sir,
Yes.
We do an introduction to calculus after seeing later.
I'm
I
speechless.
never see a thing like this. I don't sleep and wake up 3 times.
But that's the idea, right? If you come to UG and everything you see, I do that high school, this is like a walk over the bar is a joke. If you do that, well then you aren't at UG. But if you see something that puzzles you, right? Well, we are at UG, right? Yeah. So back, let me just run back that here, right? We got earlier, and again, I want if anybody takes the notes. Anybody's reading the notes and so y'all are like consulting the notes and
Yes,
say,
sir.
let me read what this guy, write and all of that. We said that, and I'll write it here, right? I'll write it here. If we have an equation, x squared plus b over a x plus c over a, right? If you write this equation in terms of its roots, it can be written like this. X squared, I think I might have to move. Good, yeah. So if we have an equation of this form, right, we can also write this equation in this form, where alpha and beta are the roots of this equation. In other words, minus alpha plus beta is really this number in front of x squared here, right? Minus alpha plus beta, I'll put it in a bracket, equal b over a. Take this over here. So alpha plus beta will be equal to minus b over a, right? In other words, what they're telling you, if you know the roots of an equation, you could know this number in front here, right? If you know the roots, add the two together and change the sign, and that's the number in front here. Is that clear? Right? You add the number, whatever the two numbers are, change the sign, and that's the number in front here. If you see what is happening, look at this. What is only. You add the two roots, and you change the sign, and that will give you this here. Right? The minus of this will give you that. Right? Let me go back to, remember we had an equation. Let's say the roots of an equation are, what did we say? Minus 2 and 3. Remember that? So we said the equation will be x plus 2, x minus 3 equals 0. When we remove the brackets, we get x squared minus x minus 6 equals 0. Look something. When we add these two numbers, what do we get?
1.
We get positive 1. If we change the sign of positive 1 and put it here, you see we get minus 1. You see how we get that? So by taking these two roots, adding them together and changing the sign, we don't get this number here. Similarly, if we take, and again here, we go back to here, alpha times beta is really the number here, C over E. Right? And it's not true what? Minus 2 by 3 gives you this number minus 6. You see that? So knowing the roots, you could cook up the equation very quickly. That's what that is saying. The only thing here with this alpha and beta and B over A and C over E is to express it algebraically. And that's what you have to wrap your mind around. Right? This is for simpletons, right? This here is for the simple-minded. Right? Where I gave you the two numbers and you can do this and remove it and get that. But can you watch these two things and tell the equation? But that's what you want to be able to do, right? And that's why we came up with this whole idea here. This whole idea here. Good. So let's go back to the solution of the problem we started off with. So we want to now write down the roots of the equation. Sorry, not the roots. We want to find the equation of itself whose roots are 1 over alpha and 1 over beta. Right? So remember, if these are the roots, then the sum of the roots, the sum of the roots of the equation we want is 1 over alpha plus 1 over beta, right? But this here, we know is 7 over 4. We found that earlier, right? So the sum of the roots is 7 over 4. So we already can start putting together equation. The equation is x squared. What are we going to do with this? We're going to change the sign, right? Remember we said that? The sum of the roots is this. So we just have to change the sign, 7 over 4x plus, well, we want a number here now, right? The product now, the product of the roots, 1 over alpha times 1 over beta is really 1 over alpha beta. Didn't we find this earlier? Yes, we found it to be half, right? Isn't that so? Look here. 1 over alpha beta, look at where this thing is going. 1 over alpha beta is a half. So we can stick in the half there, right? And you can now put your equal 0. So we have reversed engineered the equation itself, right? And what we can do now, we can multiply everything by 2. Or should we say 4? Let's go with 4. See what happens. You get 4x squared minus 7x plus 2 equals 0, right? So what you need to do is you got to wrap your head around what this is telling you, right? What this is simply telling you is that the sum of the roots of an equation is equal to the minus of the coefficient of x. That's what this is saying. From this, you get this. What? The sum of the roots of an equation is equal to minus of the coefficient of x. The product of the roots of an equation is equals to the number they ended in. That's all this is saying. We just say it with some symbols. And once you can wrap your head around this, given any root of any equation, you can reverse engineer the original equation. Everybody looks scared by it.
That's gonna take some time to digest, sir.
Yeah. Can I move this? Let me move it, or maybe I'll do one more.
Yes, sir.
I'm looking for a simple one that. All right. Let me borrow this one. Give me a second. I'll cut it from it and bring it over to you. Okay, look at this one. So you have this equation. Is this the same one we did just now? No, it's not exactly the same. The equation is the same, right? Is it?
Yes,
Yes,
sir.
sir.
The
All right,
equation.
good. Oh, good. All right. Good. So they're telling you that the roots are this, and they want you to find that equation with integral coefficients, and they mean numbers like this, don't have any fraction here, right? Whose roots are alpha over beta and beta over alpha, right? Good. So from this equation here, we rearrange it. The 2x squared minus 7x plus 4 equals 0 can be written as x squared minus 7 over 2, sorry. What am I doing? 7 over 2x plus 2 equals 0, right? So it's the same thing. So from this, alpha plus beta is really equal to 7 over 2. Remember, you're taking the minus of minus 7 over 2, right? And alpha beta is 2, right? So we got that bit from the original equation. And by now you should know how we got that. Remember we said that the sum of the roots will be the opposite of this, right? If it's minus 7 over 2, we'll use 7 over 2. The product of the root is going to be this number at the end here, right? So my friends who weren't having any clue, you get an idea now? The sum of the roots
Yes,
of
sir.
this equation
Yes,
will
sir.
be, whatever this is, just change the sign, right? And the product of the root will be this end number here. Good. Now, we got to find an equation whose roots are alpha over beta and beta over alpha. So our problem now is to do this. We got to get the sum of these roots. Alpha over beta plus beta over alpha. We got to get this. But we ain't got nothing that could give us this directly, right? We ain't got no way of doing it. So what we do is we don't sit down and just stare at the problem. could we, we hear about, man, algebraic fractions. Could I add these two things together? Let's see. So we add them together, what we get. So we get alpha, beta. Okay, beta into alpha, beta will give us alpha. Alpha by alpha, we get alpha square plus alpha into alpha, beta give you beta. Beta by beta is beta square. They look Catholic at all, right? But could that lead us somewhere? Could that lead us somewhere? Well, here's where a bit of your deep knowledge of algebra comes in, right? One of the things you can think about is, okay, this here. Let me take this here. Have you ever seen this expression? Let me say alpha beta square. What would that be equal to? It will be equal to alpha square plus 2 alpha beta plus beta square. Is that so?
Yes, sir.
So from this, and again, you would not dream of this if you're doing this for the first time, right? But if you are in the area of mathematics and you're playing around with quadratics and so, you will know that, you know what? Well, watch this thing here. This thing basically, alpha square plus beta square will be equal to alpha plus beta square minus 2 alpha beta. Can you see that? That alpha square plus beta square is really this minus this, right? So this expression up here becomes alpha plus beta square minus 2 alpha beta over alpha beta, right? And we know all of this. We know all these numbers because watch. Alpha plus beta, look, it's here. Alpha times beta, look, it's here, right? So all of that then becomes, what is it? Alpha plus beta is 7 over 2 all square minus 2 times 2 all over 2, right? And that works out to be a horrible number. I think it all works out to be 33 over 8, right? So we're going to skip the arithmetic. The hardest thing is that when you see this would stump anyone. But knowing this here, knowing this relationship, right? Knowing this relationship, you could find what is equivalent to alpha square plus beta square, right? We just have to rearrange this thing here. Good. So we now put alpha plus beta square minus 2 alpha beta in this place. And we have these numbers. We have alpha plus beta. We have alpha beta, right? We put them in there. We use our knowledge of arithmetic and we reduce it to 33 over 8, right? So that's the sum of the roots. So let's leave that down, right? So we now have to go and find what we call the product of the roots now, right? So we know that alpha over beta plus beta over alpha is equals to 33 over 8, right? 33 over 8. We got that. Leave it there. So now we have to find the product, right? Product of alpha over beta times beta over alpha is equals to 1.
1.
We can do no calculation there now. So our equation then becomes x squared. We're going to take the minus of this, minus 33 over 8x plus 1 equals 0. That's our equation. But they don't want fraction or anything. They want integral coefficients. So we multiply everything by 8. And we'll get 8x squared minus 33x plus 8 equals 0. right? So that's the equation they require, right? The equation to this thing here. So from this, you get the alpha and beta, and you have to figure out, well, what is the sum of the roots of this required equation? What's the product of the roots of the required equation? And I think what will stump everybody is this here. And the simple reason is that you have not played around with quadratics sufficiently, right? You will watch this. I think most people, when they reach here, alpha square plus beta square, how do I get that? And they wouldn't know how to move forward, right? But as I said, as you do more reading and you expose yourself to different ways of doing things, right? You'll pick up these little techniques, right? And master them, and use them to your advantage. So what I'll do, I'm going to add on a little piece. I'm going to add on a little piece to your tutorial worksheet. I'm going to, as a matter of fact, I'll just upload another worksheet that has some of this inside. Because the present worksheet that you have, I think there is some questions that deal with the nature of the roots of a quadratic equation. There are some questions there, but I don't think there are any questions on this here. So I want you to, to bend your mind a little, right? To get you thinking along new lines, right? I want you to go away and say, this UG thing and them same thing when you do a high school. No, I don't want you to get away with that, right? I have to challenge your mind, confuse you. You must pull out some of your hair from your head, get angry at me. But I'm here, you dear. You can't do me nothing. All right. So I'll stop the recording here. I know some people, they talked about blackout and so.